Okay, I want to start today with a number. And honestly, it's a number that completely stopped me in my tracks when I was reading through the stack of research for this deep dive.
I have a feeling I know which one you're talking about.
I actually had to double check it because
Yeah.
it felt wrong.
It's the big one.
38%.
Right.
38% of total global greenhouse gas emissions come from construction.
From buildings.
From buildings. It is. It's staggering.
It is, isn't it? When you really let that sink in.
It is. Because I think most of us, when we visualize climate change, we have a very specific set of stock images in our heads.
Oh, for sure.
We think about bumper-to-bumper traffic on the 405.
Yep. The smokestacks.
The smokestacks. We think about airplanes taking off, these massive factories belching out gray clouds. But we rarely look at the ceiling above us or the floor beneath our feet.
That's what some of the research calls the invisible villain paradox.
The invisible villain. I like that.
We notice the things that move. We notice the things that make noise. Cars, planes, factories, they're all active.
They're dynamic.
Exactly.
Yeah.
But buildings, they sit there, they feel benign, they feel safe.
Static.
But the reality is that the built environment is the single largest contributor to the climate crisis.
And if you want to zoom in on a specific culprit within that 38% sort of the boss battle of this problem, it's cement.
Cement is the heavy hitter, no question. Just cement production alone is responsible for 8% of all global emissions.
Okay, can we just contextualize that? Because 8% sounds like, a small slice of a pie, but in global terms.
In global terms, it's a superpower.
The superpower.
Yes. If cement were a country, it would be the third largest polluter in the world.
You're kidding.
No. Right behind China and the United States. It would emit more than India.
More than India.
It would emit more than the entire European Union.
That is wild. We are talking about the gray glue that holds our sidewalks and skyscrapers together, and it's polluting more than entire continents.
That's the one.
So naturally, we are doing a deep dive today on sustainable architecture, but I want to be really clear right off the bat because I know what happens when people hear that phrase.
They tune out.
They tune out. They think this is going to be an hour of scolding them to change their light bulbs to LEDs or telling them to slap a solar panel on the roof and call it a day.
Please no, that is the most surface level stuff. We're going so much deeper than that.
Exactly. The mission of this deep dive is to figure out how we move from those scary numbers, that 38%, to a way of building that actually, heals the environment rather than actively hurting it.
Right, from extractive to regenerative.
And the research you brought in, it's surprisingly high-tech, but also strangely ancient.
It is. It's this amazing blend. We're going to be talking about buildings that cool themselves using the coldness of outer space.
Which sounds like science fiction.
Literal rocket science physics.
Yeah.
But we're also going to talk about why 17th century settlers probably knew more about energy efficiency than most modern architects.
Okay, so let's define our terms before we get into the weeds. When we say sustainable architecture, what are we actually talking about? Because I feel like that term gets slapped on anything with a potted plant in the lobby.
It does. Greenwashing is a huge issue in the industry.
Right.
You put a bike rack out front and suddenly the building is eco-friendly.
Oh.
But formally, when we talk about sustainable architecture, we're talking about minimizing negative environmental impact.
Okay.
And you do that through a very specific philosophy: efficiency and moderation.
Moderation. That's a word you don't hear much in construction.
Exactly. Moderation in the use of materials, moderation in energy consumption, and moderation in the development space itself.
That sounds almost philosophical, like a diet for buildings.
It is philosophical.
Yeah.
And the best versions of this go beyond just doing less bad. The gold standard is what we call regenerative architecture buildings that focus on social sustainability and ecological conservation.
So not just less harm, but actually doing good.
Precisely. The goal is to ensure that our use of resources today doesn't make it impossible for future societies to survive. It's about being a good ancestor.
Being a good ancestor. I like that. Okay, so we've got a big roadmap today. We're going to unpack the history of this movement, look at the invisible carbon nobody talks about, break down the physics of free energy, and then get into the really sci-fi stuff like lab-grown wood.
It's going to be a journey.
All right, let's start with the philosophy. Because looking at the research, it seems like there was a massive shift in how we even view green buildings. For a long time, it felt like it was just an engineering problem, right?
That's a very common misconception.
Yeah.
And frankly, it was the dominant view for most of the late 20th century.
Just about the gadgets.
It was all about the gadgets. The term sustainability was viewed almost exclusively through the lens of building technology. It was about the machinery.
How efficient is this boiler?
Exactly. What is the R value of this insulation? Can we invent a better window? It was a technical problem to be solved with more tech.
Which makes sense. We love gadgets.
We do. But scholars are now shifting from that narrow technical focus to a much broader cultural framework.
What does that mean, a cultural framework?
They're looking at the human interrelationship with nature. It's not just how do we plug this heat leak.
Right.
It's how have humans related to their environment over the last 10,000 years and, where did we lose the plot?
And this actually ties back to a really interesting historical nugget you found involving Princeton University, of all places.
It does. This is a fascinating bit of, academic drama. In the 1940s and 50s, the Princeton School of Architecture played a pivotal role in reintroducing history into design training.
Wait, reintroducing? Had they banned history?
In a way, yes. You have to understand the mindset of modernism in the early 20th century.
Oh.
Think about Le Corbusier, the Bauhaus, the international style. These were people coming out of the trauma of World War I. They wanted a clean break with the past.
Right, the past was messy.
The past was messy, monarchical, and inefficient. They wanted a new world based on the machine.
The famous machine for living.
Exactly. So they rejected history. They literally stopped teaching how to build traditional roofs or thick walls. They built glass boxes that looked the same whether they were in snowy Moscow or sunny Los Angeles.
Which sounds cool aesthetically, I guess, but practically?
Practically, it was an environmental disaster.
An oven or a freezer?
A glass box in the desert is an oven. A glass box in Moscow is a freezer. The only way those buildings were habitable was because we had invented massive air conditioning and heating systems powered by cheap fossil fuels.
So I used brute force energy to fight nature.
We used brute force to correct a bad design.
So Princeton bringing history back wasn't just about nostalgia for old buildings.
Not at all. By the 1970s, you had PhD programs popping up specifically for architectural history, founded by people like Anthony Vidler at Princeton and Stanford Anderson at MIT. This intellectual groundwork helped us realize that pre-modern builders weren't primitive.
Right.
They were geniuses of adaptation. They knew how to survive without the brute force of cheap oil.
So we're looking back to move forward, but before we get to the solutions, we have to talk about this thing you called the carbon trap. You mentioned earlier that we focus on the wrong things.
We do. We have a massive blind spot. We need to distinguish between operational carbon and embodied carbon.
Okay, let's unpack that. Operational carbon sounds like the utility bill, right?
Basically, yes. Operational carbon is the energy used to run the house. The electricity for your lights, the gas for your water heater, the power for your AC.
The day-to-day stuff.
The day-to-day, and we have gotten very good at talking about this.
Yeah.
Everyone knows what an LED bulb is. Everyone looks for the Energy Star sticker on their fridge.
Right. If I leave the lights on, I feel guilty.
That's operational carbon guilt. Exactly. But embodied carbon, that's the ghost in the machine.
Okay.
Embodied carbon is the energy used to make the house.
To build it.
To build it. It's the mining of the ore, the smelting of the steel, the crushing of the limestone for cement, the transportation of those heavy materials to the site, and the actual construction.
So it's the backpack of emissions the house puts on before anyone even moves in?
That is a perfect analogy. Every single building starts its life with a carbon debt.
And here's the kicker.
For a standard new building, that backpack of embodied carbon accounts for about half of its total lifetime emissions. Half.
So all the effort we spend on efficient light bulbs and appliances only addresses half the problem.
At best. And we have almost no regulations for it. We have strict codes for how much insulation you need. That's operational. But we have almost no rules about how much carbon you can spew into the atmosphere to make the steel beams holding the roof up.
And going back to your stat about cement, that's all embodied carbon.
It is. Concrete is the most consumed substance on Earth after water. And making it is incredibly dirty. You have to heat limestone to 1,400 degrees Celsius. That requires massive amounts of fossil fuel.
Okay, so I have to ask the obvious question then. If concrete is so bad, if it's the superpower of pollution, why do we use so much of it? Are architects just lazy?
That's the tough part. It's not laziness. Concrete is. It's miraculous stuff.
How so?
It's liquid stone. You can pour it into any shape. It dries rock hard. It doesn't rot, termites don't eat it, and it's relatively cheap.
It's a silver bullet material.
It is. And replacing it is incredibly difficult because nothing else does exactly what concrete does at that price point.
So we're hooked on it.
We are addicted to it.
Yeah.
But if we ignore embodied carbon, we're missing the boat entirely. You can build a net zero house that uses zero electricity. But if you poured 500 tons of concrete to build it, you front-loaded so much damage.
That it might take 50 years of efficiency just to pay back that initial debt.
If ever.
So we need to build smarter, not just run smarter. And that leads us perfectly into the idea of passive design.
This is my favorite topic.
I know it is. And this is basically the free energy we teased in the intro. So lay it out for us. Passive versus active. What's the difference?
It's a simple definition. Active strategies use motors, pumps, fans, and plugs.
They need an external power source.
Right. Passive strategies mean the building itself does the work just by sitting there. It relies on physics, geometry, and the laws of thermodynamics.
And geometry is surprisingly important here. The research talked about the surface area to volume ratio.
This is crucial. And to explain it, I want you to think about a cup of coffee.
I am always thinking about coffee.
Good. So imagine you pour hot coffee into a tall, standard mug, and then you pour the same amount of hot coffee onto a large, flat dinner plate. Which one gets cold first?
The plate. Instantly.
Why?
Because, well, it's spread out. There's more coffee touching the air.
Exactly. The skin of the liquid is where the heat escapes. The plate has a massive surface area compared to the volume of coffee.
So more skin, more heat loss.
Right. The mug is compact.
Yeah.
It has a low surface area relative to its volume. Buildings work the exact same way.
So if I build a sprawling house with wings jutting out everywhere, what people call organic.
You are building a dinner plate.
Wow.
You are maximizing the skin of the building, which means you are maximizing heat loss in the winter and heat gain in the summer. From an energy perspective, those organic sprawling shapes are often a disaster.
So what's the mug of architecture? What's the ideal shape?
The cube, or the sphere technically, but spheres are hard to furnish.
Hard to hang pictures.
Right. So a compact, multi-story box is the most efficient shape. And this brings us back to history. The research mentions the traditional American salt box or colonial design.
You know, I always thought those houses looked that way just because of style. Like, oh, it's 1750. This is the fashion.
That is the modernist trap again.
Yeah.
We assume they made aesthetic choices. They didn't. They made survival choices.
That's a huge shift in thinking.
The salt box, shaped 2 stories, compact, boxy, was the mug. It kept the heat in around the central fireplace.
And what about the roof on those? The salt box has that distinct, long, sloping roof that goes almost to the ground on the back.
That's not style. That is aerodynamics and shielding.
Aerodynamics.
You almost always point that low, sloping roof towards the north.
Why north?
Because in New England, that's where the brutal winter winds come from. The roof acts like a shield, deflecting the wind up and over the house.
Wow.
Meanwhile, the flat 2-story side with most of the windows faces south.
To catch the sun?
Precisely. It is a passive solar machine disguised as a house.
So let's talk about catching the sun. Because facing south feels like the oldest rule in the book, but the physics of it are pretty specific.
It's all about solar gain. In the northern hemisphere, the sun is always in the southern part of the sky. In the winter, it's low on the horizon.
And in the summer, it's high overhead.
Exactly. And you want to capture that low winter sun to heat your home for free.
But windows are the weak point, right? Even a good window is basically a hole in your insulation.
Generally, yes. Glass is a poor insulator compared to a solid wall. That's why we've developed smart windows, double or triple glazing.
Which just means layers of glass.
Layers of glass with an inert gas-like argon sandwiched in between. The gas acts as an insulator, but the real magic is the low-E coating.
Low emissivity.
Right. It's a microscopically thin layer of metal oxide on the glass. It's transparent to visible light so you can see through it, but it acts like a mirror to infrared heat.
So it filters the heat?
It does. In the winter, it reflects the heat inside your house back into the room so it can't escape. In the summer, it reflects the solar heat outside back away from the house.
It's a one-way heat door. But here is the problem I see. If I have a wall of glass facing south to catch the winter sun, am I not going to roast like a chicken in July?
That is the challenge. If you don't manage it, yes, you will cook.
So how do you manage it?
This is where shading comes in.
Yeah.
And again, the best technology for this isn't a microchip. It's a tree.
A specific kind of tree.
A deciduous tree. The ones that lose their leaves in the fall.
So walk me through the seasonal cycle here.
Okay. You plant a big oak or a maple on the south side of your house. In June, the sun is high and brutal. but the tree is full of leaves.
So it's like a big green umbrella?
It blocks the sun, shading your windows.
Mm.
Your house stays cool. It's free AC.
Okay.
Then comes November. It gets cold. You want that heat. What happens? The tree drops its leaves.
And the sun comes through.
Suddenly the branches are bare, and the low winter sunlight streams right through the gaps, hitting your windows and heating your floors.
It's an automatic climate control system powered by photosynthesis.
It really is. And if you can't plant a tree, you can use things called light shelves or louvers.
The research mentioned light shelves. How do those work? They sound like furniture.
Think of a horizontal shelf sticking out from the middle of your window.
Okay.
It physically blocks the high summer sun from hitting the lower part of your window. But the top of the shelf is reflective. It bounces the sunlight up onto the ceiling of the room.
Oh, so you get the light, but not the direct heat beam.
Exactly. It throws the light deep into the building so you don't need electric bulbs, but it keeps the glare and the heat gain down. It's simple geometry, but it changes the feel of a room completely.
Okay, another term in the passive section was thermal mass. This sounds heavy.
It literally is. Thermal mass refers to heavy, dense materials like masonry, stone, concrete, or adobe.
And what does it do? Why is heavy good?
It acts like a thermal battery. Let's look at the American Southwest, all that mission-style architecture. Thick adobe walls. Why?
Because it's hot.
It's hot during the day, but in the high desert, it can get close to freezing at night. The temperature swing is huge.
Right.
The thick walls absorb that brutal solar heat all day long. It takes hours for the heat to travel through the wall, so the inside stays cool while the sun is up.
And then at night?
At night, when the air outside drops to 30 degrees, that stored heat finally reaches the inside surface of the wall and radiates into the room, keeping you warm. It flattens out the temperature curve.
So if you built that same house out of thin wood...
You'd roast by day and freeze by night. The mass is the regulator.
Fascinating. So that's passive, the building doing the work. But sometimes physics isn't enough. Sometimes you need a motor, you need a plug.
You need active systems.
Let's talk active systems. And obviously the poster child here is solar power, photovoltaics.
Right. This is what everyone pictures when they think green building. The shiny blue panels on the roof.
But I have to say, the research had a number that kind of bummed me out. It said commercial panels range from 4% to 28% efficiency. 28%. If I got a 28 on a math test, I'd be grounded. Is that good?
It sounds terrible, doesn't it?
That's awful.
A standard gas turbine might be 40 to 60% efficient, but you have to change your perspective. With a gas turbine, you are paying for the fuel. You care deeply about wasting it.
Okay.
With solar, the fuel is free. It's falling from the sky in essentially infinite amounts.
So wasting 72% of infinite doesn't matter as much.
Exactly. Even at 20% efficiency, a standard roof can generate enough power to run the house. It's about viability, not perfection. I mean, in Germany, solar is standard, and they have way less sun than most of the U.S.
But you have to point them the right way, and this gets back to geometry again.
The math of the angle. This is critical. You
Yeah.
can't just slap them on flat. You need to look at your latitude.
Why latitude?
Because latitude tells you how far north or south you are from the equator. And the equator is where the sun is, generally. You're trying to point your panels at the equator.
Okay, so if I'm in New York, that's roughly 40 degrees north latitude.
Right. So to get the best annual average, you tilt your panels at 40 degrees. That faces them directly at the average sun position over the year.
But what if I really need power in the winter, when the days are short?
In winter, the sun is low in the sky, so you need to tilt the panels up steeper to catch it.
So more than 40 degrees.
The rule of thumb is you take your latitude and add 15 degrees. So in New York, you'd tilt them to 55 degrees.
And summer.
The sun is high, so you flatten them out. Latitude minus 15 degrees.
Got it. Now let's talk about the one that breaks my heart a little bit. Wind turbines.
Ah, the rooftop wind turbine. The siren song of sustainable tech.
I see ads for these. They look so cool, like little corkscrews spinning on your roof. I always wanted one. But you're telling me they're basically lawn ornaments.
I hate to be the bearer of bad news, but for most people, yes. Small wind is a trap.
Why?
It comes down to a specific law of physics called the cube law. And honestly, if you take one hard science concept away from this deep dive, make it this one.
Okay, lay it on me. The cube law.
The power available in the wind is determined by a formula, but the important part is one variable, velocity cubed.
Cubed. So V times V times V.
Exactly. That means the power isn't linear. If the wind blows twice as fast, you don't get twice the power.
You get two
Fine.
times 2. 8 times the power.
8 times the power.
Okay. But the reverse must be true then.
It is,
Yeah.
and that's the killer. If the wind speed drops by half,
You don't lose half the power. You lose 7/8 of your power.
exactly, you are left with 12.5% of the energy. A small drop in speed is a catastrophe for output.
And where do we put rooftop turbines?
On roofs, where the wind is terrible,
I thought roofs were windy.
they're turbulent. Trees, other houses, chimneys, they all chop up the wind, they create friction. The wind speed at your roof line might be half of what it is 50 feet up in the clear.
And because of the cube law, half the speed means practically zero electricity.
You got it. So unless you live on a bald hill with 15-mile-an-hour consistent winds, don't buy a rooftop turbine. The maintenance costs alone will likely exceed the value of the electricity it generates.
Consider my dreams crushed. Let's move to something that actually works. Solar water heating.
This is the unsung hero. It's so much simpler than making electricity. You're just using the sun to get water hot.
And the research mentioned evacuated tubes, which sounds like a medical procedure.
It does, but it's brilliant engineering. Imagine a glass tube with the smaller, dark-colored tube inside it. And in between the two, nothing. A vacuum.
Like a thermos.
Exactly like a thermos.
Yeah.
A vacuum is a perfect insulator because there are no air molecules to transfer heat. So the sun hits the inner tube, heats the water to scalding temperatures, but the heat cannot escape back out.
So even if it's freezing cold outside.
The tube stays hot. These systems can be 80% efficient. Compare that to the 20% for solar electric panels. Thermodynamics loves heating water.
Okay, let's move into the belly of the beast, the HVAC system. Because eventually, passive design isn't enough. We need to heat and cool the air. And the start of the show seems to be the heat pump.
The heat pump is the most important appliance of the 21st century, period.
That is a bold claim. Explain it to me like I'm 5, because heat pump sounds like it just makes heat, but it cools too.
Think of it as a reversible refrigerator.
Okay.
Put your hand behind your fridge. It's warm, right?
Yeah.
The fridge isn't making that heat.
Yeah.
It is pumping the heat out of your food and dumping it into the kitchen.
It's moving thermal energy from one place to another.
Precisely. A heat pump does the exact same thing for your house. In the summer, it pumps heat out of your living room and dumps it outside. That's air conditioning.
Okay, that makes sense.
But flip a switch and it runs in reverse. It finds heat outside, pumps it in, and dumps it in your living room.
But this is the part I struggle with. How does it find heat outside when it's 20 degrees in January? There's no heat there. It's freezing.
That's where our human senses deceive us. 20 degrees Fahrenheit feels cold to us. But to a physicist, absolute zero, the point where there is literally no heat energy, is minus 460 degrees Fahrenheit.
Okay.
So at 20 degrees, there's actually a massive amount of heat energy in the air. It's just less hot than our skin. The heat pump can squeeze that heat out, concentrate it, and bring it inside.
So it's extracting the hidden heat from the frozen air.
Yes. And because it's moving heat rather than creating it by burning gas, it is magically efficient. A top-of-the-line gas furnace is maybe 95% efficient.
Which sounds pretty good.
It is. But a heat pump can be 300 or 400% efficient.
That sounds like cheating. How is that possible?
It feels like cheating. But it's just using the laws of thermodynamics.
Yeah.
For every 1 unit of electricity you put in to run the pump, you move 3 or 4 units of heat.
And this isn't theoretical anymore. Scandinavia is going all in on this.
Really? Because I always heard heat pumps don't work in the cold. That's the myth.
Old ones didn't.
Yeah.
Modern ones work down to negative 15 degrees. In Norway, Finland, Sweden, places with serious winters, there are now something like 25 heat pumps for every 100 people. If it works in Oslo, it works in Ohio. Fair point. Now, there's a variant of this that involves digging, geothermal.
Ground source heat pumps. This is the Rolls-Royce version.
Why dig? Why go to all that trouble?
Because the air temperature changes wildly. It's 90 in summer, 10 in winter, but 6 feet underground. The temperature is constant. It's about 55 degrees year-round, anywhere on Earth.
So it's a stable starting point.
Exactly. In winter, you aren't trying to pull heat from 10-degree air. You're pulling it from 55-degree dirt. It's much easier.
And in summer.
In summer, you aren't trying to dump heat into 90-degree air. You're dumping it in 55-degree dirt. It's way more efficient.
But expensive.
Very. You have to bring in drilling rigs. It can cost twice as much to install, but the running costs are tiny.
Okay, now we get to the part of the outline that I honestly thought was a typo. Passive daytime radiative cooling. PDRC. This section talks about harvesting the coldness of outer space. Are we building spaceships? What is happening here?
It sounds like total sci-fi, doesn't it? But this is cutting-edge physics, and it's real.
How does it work?
Okay, so we know the sun heats the Earth with radiation, but the Earth also sends heat back out into space as radiation. The problem is the atmosphere clouds, CO2, water vapor, acts like a blanket. It traps a lot of that heat. That's the greenhouse effect.
Got it.
However, there is a loophole. There's a specific frequency of infrared light between 8 and 13 micrometers wavelength that the atmosphere is transparent to.
It's like a radio window.
It's an atmospheric window. Heat at that specific frequency shoots right through the clouds, right through the air, and goes straight into the void of space.
And space is cold.
Space is incredibly cold, near absolute zero. So scientists have developed materials that are attuned to emit their heat at exactly that frequency.
So they're basically broadcasting their heat directly to the universe.
They are. And what happens to the material? It gets cold, extremely cold. These panels can cool down to below the ambient air temperature.
Wait, it gets colder than the air around it?
Even when the sun is shining directly on it.
How is that possible?
Because it's radiating heat away faster than it's absorbing it. It creates a cooling effect without using any electricity. If you cover a roof with this stuff, you can reduce AC needs by 30 to 40%.
You are essentially connecting your building to the ultimate heat sink, the universe.
Harvesting the void.
That is poetic. Okay, let's come back down to Earth, literally. Let's talk about materials. We've talked about energy, but what are we building these houses out of?
We're seeing a return to what the research calls the natural palette.
So timber, straw, stone.
The three little pigs strategy.
In a way, but we have to look at carbon again. Trees absorb carbon dioxide as they grow. When you chop a tree down and turn it into a beam, that carbon is locked inside the wood. It's sequestered. Whereas making steel or concrete creates carbon emissions.
Exactly. So a wood building is a carbon bank. A steel building is a carbon source. And then there's bamboo.
I feel like bamboo is the kale of construction. Everyone is suddenly obsessed with it.
That's a fair comparison, but the obsession is warranted. Bamboo is a grass, not a tree. It grows incredibly fast. You can harvest it for construction in 3 to 5 years. An oak tree takes 40 to 60 years.
So it's renewable on a human timescale, not a generational one.
Exactly. And it's incredibly strong. Pound for pound, it has a tensile strength that rivals steel.
And what about insulation? We're not just using that pink fiberglass cotton candy anymore.
No, thankfully. We're seeing sheep wool, we're seeing recycled denim, literally ground up old blue jeans.
I like the idea of my house wearing Levi's.
And then there's the weirdest one, mycelium.
Mushrooms.
Mushroom roots. You can take agricultural waste corn stalks, husks, put them in a mold, and introduce mushroom spores.
And what happens?
The mycelium eats the waste and grows into a dense, foam-like network that fills the mold. You bake it to stop the growth, and boom, you have a fire-resistant insulating panel that is 100% compostable.
That is wild. You're literally growing your insulation. But I have to play devil's advocate here. Just because something is natural or recycled, does that automatically mean it's good for you? The research had a section on VOCs.
Volatile organic compounds.
And this is the gotcha of green building, isn't it? Green does not always mean healthy.
It's a huge paradox. VOCs are the chemicals that off-gas from paints, glues, carpets, furniture. They cause sick building syndrome, headaches, asthma, that kind of thing.
Right.
And here's the kicker. A California study showed that some materials labeled recycled or green actually had higher toxic emissions than traditional materials.
Yeah. Oh.
Because recycled just means it was used before. It doesn't mean it's safe. And natural is tricky too. Arsenic is natural. Formaldehyde is natural. You can't just trust the vibe or the label. You have to check the specific emission standards.
So don't just sniff the cork flooring and assume you're safe. Now, we have these ancient materials like straw and stone, but the research also pointed to a very, very futuristic direction, lab-grown materials.
This is straight out of MIT. In 2022, researchers were working on growing Zinnia elegans cells in a lab.
Growing plant cells without the plant, like in a petri dish.
Yes. Think of it like lab-grown meat, but for wood. They take the cells and grow them in a gel matrix, and they can tune the properties.
Tune them? What does that mean?
They can add hormones to tell the cells to grow denser or stiffer. They can grow a specific shape like a chair leg or a beam. So there is zero waste, no sawdust, no bark.
So you could theoretically grow a wooden wall stud that is perfectly straight and never warps.
That's the dream. No deforestation, no waste. But it raises really complex questions.
Like what?
Well, if we stop harvesting forests, what happens to the rural economies that depend on timber? And strangely, what happens to wildfire management? Managed logging often helps clear underbrush. If we stop tucking forests, they just burn.
It really is a complex web. You solve one problem and you create three others.
That is the history of technology.
So before we wrap up, we have to talk about context. Because you could build the perfect house lab-grown wood, cooled by space, heated by the earth. But if you put it in the wrong place, none of it matters.
This is what the research calls the greenhouse in the middle of nowhere fallacy.
Explain that.
Imagine a LEED Platinum Eco home. It's perfect, net zero. It makes its own power, it recycles its own water. But it's located on a 5-acre lot, 30 miles from the nearest town.
So you have to drive everywhere.
Exactly. You are driving your SUV 30 miles to get a gallon of milk. The carbon emissions from your transportation will completely wipe out the carbon savings of your efficient house.
So a drafty little apartment in a dense city might actually be greener?
Almost certainly. If you live in a walkable neighborhood, take the subway and share walls with your neighbors, which insulates you for free, your carbon footprint is tiny compared to the eco-warrior in the excerpts.
This is the core idea of new urbanism.
Yes, density is green. Walkability is green. Sustainable architecture isn't just about the building, it's about where the building sits in the web of the city.
And how does water fit into that urban picture?
Cities have a huge problem with water. Concrete doesn't absorb rain.
So we get flash floods.
Right. We need green roofs.
Putting grass on the roof.
Or sedum, or gardens, or even small trees. The roof acts like a sponge, absorbing stormwater and releasing it slowly. It also insulates the building, and it fights the urban heat island effect.
That's where the city is hotter than the surrounding countryside.
Right, all that black asphalt and dark roofing soaks up the sun. Green roofs cool the entire city down.
It seems like there's a digital layer to all of this, too. The research mentions something called BIM.
Building information modeling. This is the brain of sustainable design.
Is this like SimCity for architects?
Actually, yes. That's a perfect analogy. It allows architects to build a digital twin of the building before they pour a single drop of concrete.
A digital twin?
They can simulate everything. What happens if we rotate the building 5 degrees? What happens if we use triple pane windows instead of double? What's the embodied carbon of this steel beam versus that wood one?
And the computer just spits out the carbon numbers.
Instantly. It takes all the guesswork out. You aren't just hoping it's sustainable, you know it is, because you've already simulated the next 50 years of weather and energy use.
That is incredible. We have covered a massive amount of ground today.
We really have, from top to bottom.
We've looked at the hidden carbon costs, that deadly cement. We've looked at the geometry of the sun, the coffee cup, and the salt box.
The physics of wind.
We've learned about the cube law of wind and why I shouldn't put a turbine on my roof. We've talked about harvesting the cold of space and growing wood in a petri dish.
It's a lot. But it shows that the solution isn't just one thing. It's not just technology, and it's not just going back to nature. It's a synthesis.
If you had to leave the listener with one thought to chew on, one synthesis of all this, what would it be?
I keep thinking about that contrast. The ultra-future of lab-grown plant cells versus the ultra-past of mud, straw, and stone.
Right.
And I think the most sustainable future isn't about choosing one or the other. It's about the marriage of those two.
High-tech analysis of ancient wisdom.
Exactly. We use BIM, the high-tech, to perfectly optimize the placement of a window, the ancient wisdom. We use advanced heat pumps to heat a building made of straw. We don't need to reinvent the wheel. We just need to use our new tools to make the old wheels spin better and more intelligently.
That's a great perspective. And for you listening, here's a little homework. Look at the building you're in right now. Which way do the windows face? Is that green flooring actually healthy? Start seeing the invisible flows of energy and materials around you.
Once you start looking, you can't stop seeing it. You'll be looking at the surface area of every coffee shop you walk into.
I know I will. Thanks for diving deep with us today.
A pleasure as always.
See you next time.